Hello students, welcome back. Module 10 is a continuation of Module 9, so let's begin with a review. This is the starting point of everything, the fundamental theorem. A linear ODE has a unique solution under a given initial condition. More precisely speaking, we'll have to consider the intervals of definitions, and the interval of definition must contain the starting point T0 and so on and so forth. But in any case, the real key is the existence and the uniqueness under the IC. Next, let's move on to the homogeneous case. Given homogeneous linear ODE of order n, we can always find n linearly independent solutions, y1 through yn. And furthermore, this family, y1 through yn, generates the entire solution space. That is, any solution of the original homogeneous linear ODE, L of y equals to 0, then that solution can be written as a linear combination of y1 through yn, like this. And also vice versa. Any linear combination is a solution too, but that's really trivially easy. It's the other direction. L of y equals to 0, then y is a linear combination. That's the hard part. Now, students with some strong background in linear algebra will see it like this. The first statement is telling us the existence of a linearly independent family of vectors. And the second the second statement here, the second statement is telling us that the same family generates the entire solution space. So what do we have? Linearly independent generators. What is it? What is so-called linearly independent generators? It's a basis. It's a basis. So the solution space, or in other words, the kernel of this linear operator L, has basis y1 through yn. In other words, the dimension of the solution space is n. What does that tell us? Well, the dimension is always the same no matter what kind of basis I select. So if I take different method and find different linearly independent solutions, I can always get only n linearly independent solutions at the maximum, and take the linear combination of all those, then that's going to be the general solution. Now, the students who do not possess a strong background in linear algebra, probably they didn't really understand what I just meant about dimension or solution space or kernel or and so on and so forth. Never mind. It's okay, but please remember the very last claim, the very last statement. It does not matter which method you use. If you use alternative methods to get different linearly independent solutions, you can always get n linearly independent solutions and take the linear combination of all those, then that's going to be the general solution. In other words, if you use some other method and instead of getting y1 through yn, you may get z1 through zn. You may get those. Does it matter? No, it doesn't matter actually. Any y can be written as the linear combination of these. It doesn't matter. And as for the reasoning about the basis, the uniqueness of the dimension, never mind, forget about all those. It's okay because this is not a linear algebra class. But please remember the final statement here. What does this theorem 1.2 is talking about? It does not matter which method you employ to find n linearly independent solutions. Once you get n linearly independent solutions, that's it. They will give you the general solution. Whether the general solution will be in this form, k1z1 plus dot dot dot, all the way over to knzn like this, or like this, it doesn't matter. No matter which method you use, once you get n linearly independent solutions, that'll give you the general solution. Of course, if you put those into the initial condition and get all those coefficients and then simplify all those and then compare, then of course you're going to get the same solution in the end. Okay, one more comment and then let's move on. Wronskian determinant is defined like this, and this quantity is either constantly zero or never zero. Always zero, constantly zero if y1 through yn are linearly dependent solutions, and never zero if they are linearly independent. Special case when you have second order, then the Wronskian is like this. Multiply the principal diagonal and then subtract the other diagonal like this. Okay, let's go to section 2, and this 2 is a review actually. We went through Cauchy-Euler equation already and we went through examples. But let's come back to theory a little bit. So this is a general form of the Cauchy-Euler equation. T to the nth power times nth derivative of y, t to the n minus first power times n minus first derivative of y, and so on and so forth. How do you solve it? There are two ways to do it, and my preferred method is the substitution method. It's simpler and it's easier to apply. So how do you do it? Let's begin with some lucky guess, or rather an educated guess. Y equal to t to the s power, and then take those derivatives in general like this, and then put all those back into the original ODE. So this is the original equation, and the nth derivative is just this. All you have to do is to take the derivative n times, and repeated application of the power rule is not too bad. Repeat, 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 repeat. This is the first derivative, and this is the original. You can simplify. T to the nth power, we have minus n power, and then n minus first power, and then minus n minus 1 power, and so on. T to the first power, and then minus 1 power, etc. So you'll find t to the s power common to everything, so you can factor it out. And what's left here is a polynomial of s. And that polynomial of s has degree n. This is the biggest, and there are n linear factors multiplied, so you can get only up to s to the nth power. This polynomial is called the characteristic polynomial, and if that's 0, that's what we want, because this right hand side is 0. Or t to the s power is 0. In that case, what is t to the s power? Y is t to the s power, and that's equal to 0. Oh, we get a singular solution. Y is always equal to 0. Otherwise, you have to get this characteristic equation, and you can solve it. You can solve it using the fundamental theorem of algebra. You can completely factor everything all the way down to the linear factors, and lambda can be complex. And then this has to be 0, so this has to be 0, so s equal to lambda, and we started from t to the s power, so I'm getting t to the lambda power. That much is certain. How about all the others here? Times log of t squared, log of t cubed, and so on, all the way over to n minus first power. That part is a bit unclear. But if you take that for granted, then you're going to get all those linear independent solutions, and then take those linear combination of all those linearly independent solutions. That's going to be the general solution. It looks like this. As for these, there's a bit of a hole, what can I say? But I like this computation better because the derivative computations are simpler, and then whenever you put those in, and t to the s power always pops out, and then what's left is just the expression of s. Not too bad. You can easily factor those out for relatively small degree of polynomials, and you can get those done. Now, what if you don't like this glaring hole here? In that case, maybe you'd prefer this change of variable method. I don't, but some people maybe. For example, our textbook author prefers this way, obviously, and I think that's because this part is theoretically a little bit sounder. It doesn't leave any hole. So here we go. We begin with a change of variable t is e to the x, or equivalently x is log of t. And y and z are the same function, but y is expressed in terms of t, and z expressed in terms of x. They're the same quantity, but one in terms of t, the other in terms of x, where t is e to the x, or equivalently x is log of t. So let's begin. Y of t is equal to z of x, and let's take the derivative. Y prime is equal to z prime, so far so good, but by the chain rule, we have to multiply the derivative of the inside. Derivative is x, so we multiply the derivative of the inside. What is it? What is dx dt? X is log of t, so dx dt is 1 over t here. 1 over t. Consequently, we get this. Y prime is z prime times 1 over t. So compared with taking the derivative previously by power rule, it's harder. But you can see nothing yet. Let's go to the next step, and let's take derivative here. This time you'll have to use the product rule because you have a product of two functions, this and that. Take the derivative and the derivative of the first function times the second function plus first function times the derivative of the second function. Derivative of the second function, 1 over t becomes negative 1 over t squared, so we have t squared in the denominator. How about this part? The derivative of first function, z prime becomes z double prime, fine, but by the chain rule we have dx dt again. And x is log of t, so that dx dt is 1 over t. And this 1 over t was there before, so we get 1 over t times 1 over t, so that's 1 over t squared. So we have t squared in denominator again. Put those together like this, and what's left is like this. The second derivative of this is a polynomial expression of the differential operator d up to the second derivative, or you can write like this. P2 of d is in this case d squared minus d, like this. Oh. Okay, that was sufficient for second order, but if you're on a higher order, then you have to keep going. Another derivative computation, again using the product rule and chain rule. You get this 1 over t from chain rule, and 1 over t squared was there before, consequently getting 1 over t cubed, and so on. This one goes up to third derivative, this one goes up to fourth derivative, and so on. Repeat. In general, we get case derivative like these. Put everything back to the original equation. Well, this is what we get. Nth derivative is a polynomial expression of differential operator d up to nth derivative times 1 over t to the nth power, which will kill this one off. Similar thing here, we're going to get polynomial expression, but we need 1 over t to the n minus first power. That'll kill this one off. Eventually, all those t to the whatever is gone, and we're going to end up with a homogeneous linear ODE with a constant coefficient. Goes all the way up to nth degree, so we have order n. You can solve it using the method of characteristic polynomial. Factor out characteristic polynomial all the way over to the complex number field using the fundamental theorem of algebra, and then you can express those like this. We have done it before. And then x to the j power will run from 0 to m minus 1, where m is the multiplicity, and x is log of t. So that'll give me log of t to the j power. Now how about e to the lambda x part? You can rewrite it as e to the x times lambda power, and e to the x is t, so you get t to the lambda power. So we got what we wanted, but this time foolproof. There's no hole here. Harder to understand, and of course far more difficult derivative computation with all those product rule and chain rule, but the trade-off is well, foolproof, complete solution, no hole left behind. Okay, so much for those, and then some examples here. Let's see, we went through all these examples in module 9, so let's go over this very quickly. Last one here. Okay, how about the substitution method? Okay, all right. We start from t to the s power and take the derivative. Not difficult because we are simply taking the power rule and plug all those back to the original equation. Always we have to have some power minus that, so we only have t to the s power out, and what's left has to be an expression of s, a polynomial expression of s. You can simplify that, and I simplified using computer algebra system, and that's how I got this expression here up to the 4th degree. And then how do you factor it? Again, I use computer algebra system to factor. So we got this factorization, and then this complete square. The conclusion? T to the s power is always 0, which will give rise to the singular solution, y is always equal to 0. Or, look at these factors here. S is 1, which will give you t to the first power. S is 2, that's going to give me t to the second power. And then this quadratic irreducible, or this complete square plus square, you're going to get, this is 1, so t to the first power, 1 power, cosine of square root of 2 log of t like this, and sine. That's the substitution method. Now, what if you want to do change of variable method? And the derivative computation is, of course, much harder. We begin with the change of variable. T is e to the x power, x is log of t, and y is equal to z. And we take the derivative, fine. And the second derivative using product rule and quotient rule. No, quotient rule, excuse me. Product rule and the chain rule. And the third derivative, again, product rule and chain rule. And fourth derivative, again, product rule and chain rule. Put everything here and simplify, you're going to get a homogeneous linear equation with constant coefficient. So, if you have all those derivatives, it's not too bad, but calculating all those derivatives using all those product rule and chain rule, that's the killer part. That's why I don't like this method. Otherwise, it's okay, but the derivative computation here, after here, I don't like these. It's too time consuming, too labor intensive. Anyway, from here it's easy. Factor it, and then we have exponentials and exponentials with sines and cosines, and then change those back to the change of variable here. T is e to the x, t is e to the x, and x is log of t. So we get all that. And if you use a change of variable method, you're going to be leaving out y is constantly equal to 0, that thing. So artificially add one more solution here, the singular solution. As for change of variable method, if you like it, go ahead and use it. Our textbook author does it that way. But personally, I prefer to use substitution method because the derivative computation is a lot simpler. I can handle it in one line, while the other one I had to spend something like 5 or 6 lines. Okay, so much for example problems, and we went through all those theory parts. Let's begin section 3 in a separate video.